Thanks. It's great to be here today. So today I'd like to talk to you guys about some deep learning, generative models by leveraging domain-specific knowledge from vision. So we recently known that supervised neural nets have been doing really good performance in vision applications, speech, as well as NLP. But today I'd like to talk to you guys about another set of deep learning techniques. These are called latent generative models. And with these generative models, hopefully we can learn very semantically meaningful features. And specifically, I want to talk about different methods to add structure to them. And by structure, I mean building in meanings of these latent variables. Instead of having just learn everything from scratch, we want to be able to give some meanings. So 3 models I'd like to discuss today. The first one is what I call the robust Boltzmann machine, which helps us to be able to generalize to better deal with occlusion and noise. Deep Lambertian networks for illumination variations within the image. And finally, learning with visual attention, which should help us with learning generative models on a big image. So how do we better deal with noise inclusion that we see every day in the natural environment? And the way we do it is we introduce binary hidden variables to existing Boltzmann machines. And I'll go into it just but before we get started. Let's quickly review the restricted Boltzmann machines. These things are at the intersection of statistical mechanics and computer science, and they've sort of been responsible for rekindling the interest in deep learning around 10 years ago. And we can use them to learn very nice features from raw data. And they're also a proper probabilistic density model of the data. So the problem with these models is that if we train them on faces, and then we look at and then during test time, if there's a occluder, then their performance decreases dramatically. These are gnats, so there's a huge difference, even though the proportion of occluded area is the same. So that's not a good property to have. And our natural solution for this problem is one natural solution is to be able to clamp the areas which is clean or there is no noise, and let the model impute or fill in by using it's learned prior in the areas which are occluded. So this is what we're going to do. It's very natural. So how do we do it in terms of the actual model? What we can do is we can, instead of having one random variable per pixel like you would normally have, we can now simply add 3 for every single pixel. Here you have the noisy image V tilde, the clean V, and also the binary mask S. So if you have something like this, then the binary variable S can sort of gate off the interactions between the noisy image and the clean image that the model prefers. And this allows it to seamlessly handle occlusion. So here are some results of the model. So the top row of the top row here is the observed image V tilde, and the middle and the bottom row are what the model can infer after training what it sees. So in this case, it's trying to figure out what the clean face will look like given a noisy face. And what is also more surprising is that we're able to also learn a statistical prior on the occluder shape. So on the bottom row here, the top panel consists of a grid-like occluding pattern. And on the bottom, it's the sunglasses could be considered as an occluder. And so it's able to, so this framework can holistically learn to separate out between the clean image and the noisy occluder. We can also do, with a generative model, one thing we can do is we can fill in missing data. In this case, we can do denoising. So if there's a noisy pattern, we can fill in what the model thinks should be behind the occluder. Same thing for salt and pepper noise. So we can do it much better than other methods because this new model can clamp onto the pixels, which it thinks it should be noise-free. And we can also do better in terms of recognition because the latent variable, it's sort of clean, so we can figure out if the sunglasses and the scarf are not part of the training data set, the data set of the training part of the training set, we could remove the occluder and then do recognition at this stage, and we get better performance numbers. So that's the first model. The second model I wanted to discuss today follows on the same lines. It's what I call the deep Lambertian network. It's able to, the first model deals with the occlusion noise. This model deals with the illumination. So it's called Lambertian network because it follows from the Lambertian model in image processing. Essentially, it says that the pixel intensity you observe in your picture is going to be related to the lighting direction as well as the surface normal of a 3D surface. And also the albedo, which you can think of as a sort of a paint coefficient. Now, we want to be able to build this semantics or this into the deep network, which doesn't really exist before. So we use something called a deep Boltzmann machine or deep leaf network. And what we have here is in our models, we have three latent variables: the lighting direction, the surface normals, and the albedo, as part of the latent variable, the first hidden layer you can think of this of the generative model. And we built in that, we specified that ahead of time. And now we have a deep leaf network on this stream, and a deep Boltzmann machine or deep leaf network on albedo, and then a Gaussian prior on the lighting direction. This is three-dimensional. And they generate the observed image, V, using this Lambertian reflectance assumption by this equation, just what I showed you on the last slide. So this whole thing is built in. And what we're interested in at inference time is we're interested in condition on, given a V image, a face under lighting conditions, just one image, we want to be able to figure out what is the lighting direction, which direction is light coming from, what is the albedo, and what is the surface normal, given only one image. And the only way to do that is that if we're able to successfully learn a statistical prior of the surface normals and albedo, can we do that? And so this is the model. We can train it using MCMC techniques. So we play with a data set with severe lighting conditions, as you can see, different levels of lighting variations. And after training, here's how we do inference. So condition on a test image V under lighting shadows from the left side, we can the model very quickly, during posterior inference, jumps into the correct mode by about 5 Gibbs iterations. And here, the color image is the surface normals because it's three-dimensional, so we plot this as a RGB image. So this is a good result for inference. And we can also do it for other test images. So here on the left column are test subjects. And using the technique of the last slide, we could infer the albedo and surface normal. And given the inverse albedo and surface normal, we can relight, which means that we can randomly choose a lighting direction and see what the model will synthesize. And they look pretty good. So it demonstrates that the model actually really did indeed capture the semantics of the object just by given one single image. Same thing, in one-shot face recognition results, we do better than standard algorithms. Okay, so that's the second model. The third model I want to discuss today has to deal with how do we use visual attention to learn from a big image. So right now, it's really hard to learn a really good generative model on a big image just because of the complexity of the scene. But sometimes we only care about a very small object within the image. For example, we care about the face, and we don't care about the background. And so how do we use visual attention to focus on the area we really care about within a probabilistic framework? So here is our model. We have a generative model on top, and then we have attention, which interacts with the learned face variable with the big image. Here it's doing inference, it's showing the inference. So we start off with the yellow box randomly placed, and attention quickly can shift to the area of interest, in this case, the face. For this model, we use the Gaussian deep leaf network, and here right now the movie is showing the process of drawing random samples from the deep leaf network. You can think of these as sort of very primitive neurons, and they're sampling the manifold of faces trained. So it's giving good generative results. So this is going to be our generative model. We also have taken inspirations from the shifter circuit. This is a computational neuroscience model from the 90s. And what this does is that says that there's in the brain somewhere the theory it's proposing to have an object-centered reference frame of representation. And when your object in the retina shifts in scale and position, there's a dynamic routing that routes information to the canonical object reference frame. So this representation is always going to be invariant of transformations. And then associative memory can handle much better handle invariant representation. So we take sort of inspiration, we replace the associative memory with a deep leaf network, as you see here. Then we have the object-centric reference frame is corresponds to the visible units. And 2D similarity transformation from geometry is used to shift around this sort of attention window. And this is our probabilistic framework, which is a proper probabilistic model, but only models of a small patch X of view instead of a big image, and that's why we're able to do it. However, there's some difficulties. If you want to try to perform inference in the framework using a traditional method like hybrid Monte Carlo, we might get stuck. And this is due to the fact that HMC is similar to face alignment algorithm. So it's here, and for those of you who works with computer vision, you know that this is a common problem with the alignment algorithms. So how do we make sure that inference is efficient and we can make large jumps in posterior space? And we can use a convolutional neural net for this by making an approximate inference proposal network. It's a separate stream going upwards. And what we do is we take the visible V as an input to one stream, the input of the convnet. Then we take a context window in the yellow as another input. And the network spits out, the output of the network, of this inference network, tells us where we should focus on next, the change in the gaze direction. Once we obtain that, we can then use the updated transformation parameters to then feedback and gate or shift attention to the updated location as you see the jump. So this whole thing can be repeated many times, a few times, 5 times, and the whole thing repeats, and we quickly shift our attention right to the area of interest. So after we have a good proposal, we can use HMC, and this is we want to do that because this is a proper MCMC algorithm, so we can draw samples. But this only makes fine adjustments. The bulk of work is done by the approximate inference by the convolutional neural net. So that's the inference. Now, what we're really interested in is how do we do learning? So learning means that how are we able to leverage a large set of big images to learn novel faces. So for this, we could use the EM algorithm. So the E step, we use the inference to give us good localization. And then in the M step, we can use to update the parameters of the Gaussian deep leaf network. For experiments, here's some more inference experiments. These are test images, so you can see that across different backgrounds and different initialization, this method is very robust and jumps very fast to the able to localize the face in a few approximate inference iterations. And for learning, what we're able to do is we can these are samples from the generative model or framework trained on Caltech faces, the data set. And we can use the EM algorithm to learn on another data set, the CMU faces. And then on the right here are the samples from the model after we train it on both data sets. And highlighted in green shows that our model sort of adapts to both distributions. We're able to learn from both data sets by using this technique. And finally, a model is a probabilistic model, so we can actually do, when we do inference, unlike standard face detectors, we can choose where to focus depending on what the latent V is. So in this case, the model is the same, the test image is the same, the initialization is the same, but where we choose to focus is different because the setting of the canonical face object representation is different. So in this case, on the left, we can focus on to the female subject on the left. And on the second example, we focus on to the male subject on the right because these two are different. So essentially, where to attend to is a function of what the probabilistic model has in mind. Okay, so in conclusion, we proposed this talk is about generative models. Even though it's not as sexy at the moment, it's still it's a very interesting area of deep learning. And these three models, we've tried to strike a good balance between hand engineering and also learning everything from scratch. And these three things allows us to better deal with noise inclusion, illumination, as well as using visual attention to focus on an area of interest. So thank you.